The briefing room at Damascus Air Base fills with cigarette smoke as Syrian Air Force pilots gather in the pre-dawn darkness of June 9, 1982. Major Adnan pulls on his flight suit, the fabric still damp from Lebanon's humidity, and studies the tactical map spreading across the metal table. Red circles mark Israeli positions in the Bekaa Valley. Blue arrows show the planned intercept vectors. Everything looks exactly like the exercises they've flown 100 times, with Soviet advisors watching from the tower. The intelligence officer taps the map with his pointer. Israeli F-15s and F-16s operating over the valley. Standard cap patterns. We have numerical advantage, 3 squadrons to their 2. The math feels reassuring. Syrian MiG-21s and MiG-23s have patrolled these same skies for years. The Soviet doctrine manual sitting on every pilot's shelf promises that proper formation discipline and ground-controlled intercept procedures will neutralize any technological disadvantage. Major Adnan has memorized every page. Outside, ground crews fuel the MiGs, while the eastern horizon begins its shift from black to gray. The maintenance logs show green across the board. These aircraft represent the latest Soviet export models, the MiG-23ML with its improved radar, the nimble MiG-20s that Damascus received just 18 months ago. Syrian mechanics have trained in Soviet factories. Syrian pilots have logged hundreds of hours in Soviet-designed simulators. The system works because Moscow designed it to work. Nobody in that briefing room knows that Israeli pilots are already strapping into cockpits 30 miles west, their aircraft connected to a battlefield network that will turn the coming engagement into something resembling execution more than combat. The Hughes AN/APG-63 radars in those F-15s are already spinning, their pulses penetrating the dawn haze to paint Syrian formations before Syrian pilots have even started their engines. Major Adnan climbs into his MiG-23's cockpit as the sun breaks the horizon. His radar warning receiver sits quiet. His radio crackles with the familiar voice of the ground controller at Damascus, calling out vectors and altitudes in the practiced rhythm of Soviet intercept doctrine. Everything feels normal. The engine spools up with its characteristic whine. The gauges read nominal. He taxis into position behind his wingman, throttles forward, and lifts into the Lebanese morning with the absolute confidence that comes from flying a system designed by engineers who beat the Germans, who put the first man in space, who built an air defense network that spans 11 time zones. The mission is simple. Patrol assigned sectors, wait for ground control to vector them onto targets, execute the intercept profile exactly as practiced. Soviet doctrine eliminates uncertainty through rigid procedure. Syrian pilots don't freelance. They don't improvise. They follow the system that has protected Arab air forces since 1955. Major Adnan levels off at assigned altitude and switches his radar to search mode. The scope shows the expected clutter, ground returns, weather, the electronic noise that always fills the Bekaa Valley. He waits for ground control to call the vectors that will guide him onto the Israeli fighters their surveillance radars have surely detected. His finger rests near the weapon selector. His wingman holds perfect formation 500 meters to his right. Everything proceeds according to doctrine. The radio crackles. Ground control sounds unusually urgent. Major Adnan Banks left to follow the new heading, his MiG responding exactly as Soviet engineers promised it would. He has no idea that he's already been dead for 90 seconds, tracked, locked, and designated for elimination by a radar system that can watch him and 5 of his friends simultaneously, while the American-trained Israeli pilot drinking coffee 30 miles away decides which one to kill first. The first AIM-7 Sparrow leaves its rail at 8:14 a.m., covering the distance in 18 seconds. Major Adnan sees nothing. No launch flash, no contrail, no radar warning. His MiG-23 simply disintegrates around him, the warhead's expanding rod pattern shredding hydraulics and control surfaces before his brain can process what's happening. The ejection seat fires automatically. He's floating under canopy when his wingman explodes 500 meters away. Then 2 more MiGs behind them, all within 40 seconds. The radio erupts into chaos. Damascus ground control screams vectors that made sense 3 minutes ago, but are now catastrophically outdated. Syrian pilots bank hard, their radars showing nothing but clutter, while Israeli F-15s circle 15,000 feet above them, their Hughes radars calmly tracking every defensive maneuver. The Americans designed this system around a simple principle: see first, shoot first, survive. Syrian MiGs are flying blind into a shooting gallery where the shooters can see in the dark. Captain Rifat manages to get his MiG-21's radar locked onto something, maybe an Israeli F-16, maybe a ghost return. He'll never know. He squeezes the trigger. His R-60 missile drops away, motor igniting, then corkscrews into the ground as Israeli jammers flood the frequencies his guidance system needs. 3 seconds later, an AIM-9 Sidewinder tracks his engine heat signature and ends his war. His last radio transmission is just static and a half-formed word. By 8:30 a.m., 16 Syrian aircraft are burning wreckage scattered across the Bekaa Valley. Israeli pilots are reporting target-rich environments, their American radars presenting neat columns of data showing range, altitude, closure rate, and optimal firing solutions. One F-15 pilot will later describe it as like practice intercepts, except the targets don't come home. The Syrian formations are dissolving, pilots breaking in all directions, some heading for Damascus, some simply trying to survive the next 60 seconds. Damascus ground control has lost any pretense of managing the battle. Their Soviet-built radar screens show aircraft disappearing in clusters, the surveillance picture collapsing faster than human operators can comprehend. They call vectors to pilots who are already dead. They order engagements against Israeli formations that have already moved 20 miles. The doctrine assumes the ground controllers can see the battlefield. Instead, they're watching their air force evaporate in real time, while Israeli data links are sharing targeting information across formations faster than Syrian ground radar can refresh its displays. Lieutenant Bashir ejects over friendly territory after his MiG-23's engine quits. Whether from battle damage or mechanical failure, he'll never know. He watches 3 more Syrian fighters fall during his parachute descent, black smoke trails marking their terminal dives. The sky that was full of friendly aircraft 15 minutes ago now contains only the distant silver specks of Israeli jets circling unmolested, their pilots selecting targets like shoppers choosing produce. By 9:45 a.m., it's over. 82 Syrian aircraft destroyed. 0 Israeli losses. Israeli pilots are reporting Winchester out of missiles and returning to base to rearm for afternoon sorties. Syrian ground crews at Damascus count the aircraft that return and realize with sick certainty that most of their squadrons are simply gone. The maintenance officers who signed off on those aircraft 2 hours ago now face the impossible task of explaining to Soviet advisors how their doctrine failed so completely. Major Adnan, still tangled in his parachute in a Lebanese field, watches Israeli F-16s streak overhead and understands with absolute clarity that everything he learned about air combat in Soviet training schools has just become obsolete. The confident predictions in that morning's briefing, numerical advantage, proper formation discipline, proven Soviet systems, died with 81 of his countrymen before lunch. American engineering just rewrote the rules. The humiliation starts in 1965 when American F-4 Phantoms begin falling out of Vietnamese skies in numbers that horrify Pentagon planners. These aircraft cost $3 million each and carry radar systems that weigh more than entire World War II fighters, yet North Vietnamese MiG-17s, subsonic designs from 1950, are shooting them down in turning fights where speed and missiles mean nothing. The Air Force watches gun camera footage of Phantoms bleeding energy in vertical scissors maneuvers, their pilots trained for beyond visual range intercepts, suddenly forced into dogfights they can't win. Major John Boyd sits in a Pentagon office in 1966, covering whiteboards with equations that will eventually revolutionize fighter design. He's developed energy maneuverability theory, a mathematical framework that reduces air combat to rates of energy gain and loss. His calculations prove what Vietnam is demonstrating brutally. The F-4 bleeds energy in turns faster than it can regain it, creating windows where even inferior aircraft can kill. Boyd's equations show that future fighters need sustained turn rates above 10 degrees per second, an acceleration that replenishes energy as fast as maneuvering depletes it. The Air Force issues its FX, Fighter Experimental Requirement, in 1967, demanding an aircraft that can outmaneuver anything Soviet engineers might design, while maintaining the beyond visual range capability that Vietnam proved essential once you actually achieve air superiority. McDonnell Douglas wins the contract in 1969 with a design that looks impossibly aggressive. Twin tails, shoulder-mounted wings, twin Pratt & Whitney F-100 engines producing 25,000 pounds of thrust each. The engineers are building a Mach 2.5 aircraft that can also pull 9 Gs in sustained turns without bleeding the energy that kills pilots. The prototype YF-15 rolls out of St. Louis in June 1972, painted in blue and white test colors that will never see combat. Chief Test Pilot Irving Burroughs straps in for the first flight on July 27th. The twin F-100 is spooling up to a combined 50,000 pounds of thrust. The aircraft lifts off after just 900 feet of runway, a fighter that weighs 40,000 pounds behaving like something half that size. Burroughs pushes it through basic handling, reporting control responses that feel instantaneous, acceleration that pins him into the seat, and stability that makes formation flying feel natural. The engineers have solved problems that Soviet designers don't even know exist yet. The F-15's wing loading, aircraft weight divided by wing area, produces exceptional maneuverability without sacrificing high-altitude performance. The thrust-to-weight ratio exceeds 1.1, meaning it can accelerate while climbing straight up. Boyd's energy maneuverability equations guided every curve of the airframe, creating a fighter that gains energy faster than it loses it across the entire flight envelope. But McDonnell Douglas engineers understand that pure performance means nothing without sensors that can use it. They integrate the Hughes AN APG-63 radar into the F-15's nose, giving pilots the ability to track multiple targets while maneuvering, something no previous fighter radar could manage. The weapons system can launch missiles at 6 different targets before any of them know they're being engaged. The Soviets are still designing radars that require straight and level flight to maintain lock. The first operational F-15A enters Air Force service in January 1976 at Langley Air Force Base. Its pilots reporting an aircraft that feels alive, that responds to thought more than stick pressure, that turns Mach 1.5 intercepts into routine procedures. Production accelerates through the late 1970s. Israel requests export versions in 1976, receiving its first F-15A BAZ, Hebrew for Falcon, in December 1976. Israeli pilots transitioning from French Mirages report that the American fighter doesn't just outperform its predecessor, it represents a completely different category of weapon system. They have no idea they'll prove it over Lebanon in 1982. The Hughes Aircraft Company radar engineers working in Culver City, California in 1970 face a problem that has frustrated fighter designers since radar entered combat: ground clutter. Conventional pulse radars send out a signal and listen for returns, but they can't distinguish between an enemy fighter at 20,000 feet and a hillside 30 miles away. Both reflect radar energy. Both appear on the scope. Pilots scanning low-altitude targets see a screen full of useless noise, while the aircraft they're hunting hides in the electromagnetic chaos. Engineer Tom Amley leads the team developing pulse Doppler technology for the AN APG-63, working in a laboratory where oscilloscopes display the radar returns that determine whether pilots live or die. Pulse Doppler exploits the Doppler effect, the frequency shift that occurs when radio waves bounce off moving objects. A fighter traveling 600 m toward the radar source returns a signal with a measurably different frequency than stationary ground features. AMLI's circuits filter out anything that isn't moving, turning that cluttered scope into a clean display showing only airborne targets. The first test unit goes airborne in 1972, mounted in a modified F-4. The radar operator watches ground returns vanish from his display as the Doppler filters engage, leaving only the chase aircraft flying the target profile. The system tracks that aircraft through valleys, over ridges, against terrain that would blind conventional radar. More importantly, it does this while simultaneously tracking 5 other targets, the computer sorting returns and maintaining individual tracks on aircraft separated by miles of sky. Hughes engineers integrate track-while-scan capability that makes the AN/APG-63 fundamentally different from Soviet designs. Previous fighter radars could track one target or scan for many, not both. The Soviet RP-23 radar in the MiG-23 requires pilots to choose between search mode and track mode, creating deadly gaps in situational awareness. The Hughes system scans continuously while maintaining track files on up to 6 targets, updating each track 4 times per second. The pilot sees a tactical display showing range, altitude, closure rate, and weapon firing parameters for every threat within 100 miles. The system's computer, a Texas Instruments unit that weighs 65 pounds and draws 115 watts, performs calculations that would require 3 ground-based mainframes in 1960. It predicts target positions based on velocity vectors, calculates optimal intercept geometries, determines which targets pose immediate threats, and presents firing solutions that account for missile flight time and target maneuvers. An F-15 pilot facing 6 enemy fighters receives a display showing which targets are in range, which weapons should engage each target, and the probability of kill for every shot. The Israelis received their first F-15As with AN/APG-63 radars in 1976, and Israeli pilots begin training against the system's capabilities. They quickly realized that engagements are no longer contests between pilots. They're competitions between sensor systems. The side that sees first establishes the terms of battle. The side that can track 6 targets while maneuvering can fight outnumbered and win. Syrian pilots training in Soviet simulators are learning to fight battles where everyone sees the same things at the same time. Israeli pilots are learning to fight battles where they see everything and the enemy sees nothing. By 1982, Israel has integrated the AN/APG-63 into a broader network that shares radar tracks across formations via Elbit-designed data links. An F-15 radar picture becomes available to every Israeli fighter within 50 miles. Syrian pilots still rely on ground controllers reading surveillance radars that update every 6 seconds and can't see through ground clutter. The technological gap isn't about speed or maneuverability. It's about information. American engineers gave Israeli pilots the ability to see the battlefield in real time, while Syrian pilots fly blind into kill zones, their Soviet radars painting useless ground returns while missiles close from angles they never detect. General Dynamics engineers in Fort Worth face a completely different problem in 1972. The F-15 is working too well. At $18 million per aircraft, the Air Force can't afford enough Eagles to defend every airbase, every strike package, every close air support mission. They need a cheaper fighter that can handle the missions that don't require the F-15's full capability, a lightweight aircraft that trades some performance for numbers. The requirement lands on Harry Hilliker's desk, and he starts designing what pilots will eventually call the electric jet. Hilliker's team builds the YF-16 around a single Pratt & Whitney F-100 engine, the same power plant that gives the F-15 its performance, but wraps it in an airframe that weighs 12,000 pounds less. The result is a thrust-to-weight ratio that actually exceeds the F-15's, creating a fighter that accelerates like a rocket and sustains 9G turns indefinitely at combat weights. The first prototype flies on January 20th, 1974. Test pilot Phil Ustricher reporting handling characteristics that make aggressive maneuvering feel natural. But the revolutionary element isn't the airframe. It's the flight control system. Hilliker's engineers eliminate the mechanical cables and hydraulic boosters that have controlled aircraft since the Wright brothers. Instead, they install a fly-by-wire system where pilot stick inputs travel as electrical signals to computers that translate human intent into control surface commands. The F-16 is actually aerodynamically unstable. Left to itself, it would tumble. The computers make hundreds of corrections per second, maintaining controlled flight while giving pilots maneuverability that stable designs can never achieve. The design includes a side-stick controller positioned on the right console, where a pilot's hand naturally rests during high-G maneuvers. Conventional center sticks force pilots to brace against G-forces while moving the stick through large deflections. The F-16's side stick requires almost no movement. The strain gauges inside measure pressure rather than position, translating a 2-pound push into a 9G turn. Pilots report that the aircraft responds to thought, that the computers anticipate what they want before conscious intent becomes physical action. General Dynamics delivers the first production F-16A to the Air Force in January 1979. The Israelis ordered their first batch that same year, receiving aircraft modified with Israeli avionics and weapon systems. Israeli pilots transitioning from A-4 Skyhawks, subsonic attack aircraft from the 1950s, find themselves flying a fighter that climbs at 50,000 feet per minute and carries the same APG-66 pulse Doppler radar technology that makes the F-15's Hughes system so lethal. The lightweight fighter concept has produced an aircraft that performs air superiority, close air support, and strike missions equally well. The Israelis integrate Python 3 and Schaefer missiles onto their F-16s, combining American airframe technology with Israeli weapons that have already proven effective in previous conflicts. They add ECM pods that jam Syrian radars across multiple frequencies. By 1982, Israeli F-16s carry targeting pods that allow precision strikes against ground targets, then transition immediately to air combat using the same radar systems that give F-15s their beyond visual range advantage. The F-16's operational cost proves exactly what Hilliker's team predicted: half the F-15's per flight hour expense, allowing Israel to maintain larger standing patrols and more aggressive training programs. Israeli pilots are logging twice the flight hours of their Syrian counterparts, practicing the high-G maneuvers and radar intercepts that the fly-by-wire system makes possible. Syrian pilots are still learning Soviet doctrine in stable, mechanically controlled aircraft that require perfect technique to avoid departing controlled flight. When Israeli F-16s launched for the Bekaa Valley on June 9, 1982, they're carrying the same beyond visual range missiles, the same pulse Doppler radars, and the same data link integration that makes F-15s so dominant. The lightweight fighter concept has produced a weapon system that Syrian pilots literally cannot distinguish from the larger F-15 until it's too late. The Elbit Systems engineers working in Haifa in 1980 are solving a problem that American designers never anticipated: how to make American fighters even more lethal by connecting them into a network that shares information at electronic speeds. The Israeli Air Force receives American aircraft but not American doctrine, and Israeli commanders understand something the Pentagon is still learning. Individual fighter performance means nothing if pilots are operating on outdated information. The solution becomes the Elbit C3 data link system that turns formations into hunting packs, sharing a single tactical picture. The data link hardware fits into a pod mounted on the F-15's centerline pylon, containing a transmitter receiver that broadcasts encrypted radar tracks across UHF frequencies. When an Israeli F-15's AN APG-63 radar detects a target 80 miles away, that track appears simultaneously on the displays of every Israeli fighter within 50 miles. The formation commander sees what every radar sees, building a composite picture that eliminates gaps in coverage and allows coordinated engagements against superior numbers. Syrian pilots operating under Soviet doctrine receive vectors from ground controllers who are looking at 6-second-old radar pictures. Israeli pilots are making decisions based on information less than 1 second old. The network integration goes deeper than just sharing radar tracks. Israeli ground-based Hawkeye early warning radar stations in northern Israel scan 200 miles into Lebanon, their powerful surveillance radars detecting Syrian formations as they take off from Damascus. Those tracks feed directly into the data link network, giving Israeli fighter pilots threat information before Syrian aircraft even reach the combat zone. The Bekaa Valley becomes a kill box where every entry point is monitored, every Syrian formation pre-targeted before they know a battle has started. Israeli commanders position F-15s in high cap, combat air patrol, stations at 30,000 feet, while F-16s orbit 10,000 feet lower, creating a layered defense where American pulse Doppler radars have overlapping coverage across every altitude band. Syrian formations climbing to intercept altitude appear on Israeli screens while still 60 miles away, tracked continuously as they maneuver, their courses predicted and intercepted before Syrian ground controllers can update vectors. The data link system transforms individual engagements into coordinated executions, where 4 Israeli fighters can engage 12 Syrian aircraft simultaneously, each pilot knowing exactly which targets his wingmen are handling. The Israelis add another American technology that magnifies their advantage, the E-2C Hawkeye airborne early warning aircraft. Israel receives 4 of these turboprop aircraft in 1981, each carrying an AN/APS-145 radar in its distinctive rotating dome. The Hawkeye orbits over Israeli territory, its radar scanning 250 miles in every direction, tracking every aircraft over Lebanon and western Syria. The radar picture flows directly into the Elbit data link network, giving Israeli fighters complete situational awareness across the entire battlefield. Syrian pilots climbing out of Damascus have no idea that an American-built radar aircraft circling 50 miles inside Israel is already tracking them, that their courses and altitudes are being broadcast to Israeli F-15 pilots who are calculating intercept geometries before the Syrian ground controllers have even assigned patrol sectors. The Soviet air defense system assumes that ground-based radars provide adequate surveillance. The Israelis have built a system where airborne radars, ground stations, and fighter radars combine into a network that sees everything. On June 9, 1982, this integration produces results that seem impossible to Syrian commanders analyzing the battle afterward. Israeli pilots are reporting enemy positions that Syrian ground controllers haven't detected yet. Israeli missiles are launching from angles that Soviet doctrine says should be blind spots. Israeli formations are coordinating attacks across 40 miles of airspace with precision that requires real-time information sharing. The Syrians are fighting with 1960s coordination doctrine against an enemy that's achieved 1980s network-centric warfare. The technological generation gap isn't measured in aircraft performance. It's measured in how quickly pilots can share what they know. The Syrian SAM, surface-to-air missile, network spreads across the Bekaa Valley, like a web designed by Soviet engineers who learned their trade-stopping German bombers over Stalingrad. 19 SA-6 batteries, 8 SA-2 sites, and 2 SA-3 complexes create overlapping engagement zones that should make Israeli air operations suicidal. The SA-6 Gainful represents Moscow's most advanced export technology, a mobile system with semi-active radar homing that's killed Israeli aircraft in previous conflicts. Syrian battery commanders run their systems exactly according to Soviet doctrine. Radars sweeping assigned sectors, missiles ready on launchers, crews trained to engage targets the moment they enter range. Israeli mission planners studying reconnaissance photos in Tel Aviv understand that achieving air superiority over Lebanon requires destroying this network before Syrian fighters can use it as cover. American doctrine from Vietnam provides the template. suppress enemy air defenses first, establish air superiority second, conduct strike operations third. But the Israelis add technologies that didn't exist in 1972, creating a suppression campaign that combines unmanned decoys, electronic warfare, and anti-radiation missiles into a coordinated strike that begins at 2:40 p.m. on June 9th. The first wave consists of IAI scout drones, small unmanned aircraft carrying radar reflectors that make them appear fighter-sized on Syrian surveillance screens. Syrian battery commanders watch their radar scopes fill with targets and begin illuminating them with guidance radars, feeding targeting information to their SA-6 missiles. What they don't know is that Israeli F-4 Phantoms orbiting 30 miles away are carrying AGM-78 standard anti-radiation missiles, American weapons specifically designed to home on radar emissions. The moment a Syrian guidance radar activates, it becomes a beacon guiding a missile to its own destruction. The AGM-78's launch, their seekers locking onto SA-6 guidance radars, transmitting at 10 gigahertz. The missiles cover the distance in 90 seconds, their 215-pound warheads detonating directly over radar vans that contain the electronics controlling entire batteries. Syrian crews watch their displays go blank, then feel the shock waves as American weapons turn their vehicles into burning wreckage. Battery commanders try switching to backup radars only to watch those systems die as well. More AGM-78s tracking the new emissions and eliminating them before crews can even traverse the antennas. Israeli F-16s follow the anti-radiation missiles, carrying GBU-15 electro-optical guided bombs that allow precision attacks from outside SA-6 range. Syrian battery commanders who survived the first wave watch TV-guided bombs impact their transporter erector launcher vehicles with accuracy that makes visual aiming look primitive. The Israelis are using television cameras mounted in bomb noses to guide weapons directly onto parked missiles, destroying launchers before they can fire a single shot. The electronic warfare dimension adds another layer of chaos. Israeli aircraft carry ALQ-99 jamming pods that flood Syrian radar frequencies with noise, making target tracking impossible even for batteries whose radars survived the initial strikes. Syrian operators see their screens wash out into static, the carefully calibrated Soviet systems overwhelmed by jamming power that exceeds their design parameters. Some batteries launch missiles blind, hoping Soviet command guidance will steer them onto targets. The missiles climb, lose lock, and self-destruct according to safety protocols built into their programming. By 4 p.m., 29 of the 30 Syrian SAM batteries are destroyed or abandoned. Israeli fighters are orbiting over the Bekaa Valley unmolested, their radars detecting no enemy SAM emissions, no guidance signals, no threats. The survivors, Syrian crews who watched their comrades die around them, are shutting down their radars and retreating toward Damascus, understanding that transmitting means dying. The Soviet air defense network that took 3 years to install and integrate has been eliminated in 2 hours by a combination of American anti-radiation missiles, precision-guided weapons, and electronic warfare that Soviet designers never anticipated facing simultaneously. Lieutenant Colonel Jamal sits in a Damascus debriefing room 3 days after the battle, his flight suit still smelling of smoke and jet fuel, trying to explain to Syrian intelligence officers how his entire squadron disappeared in 12 minutes. He flew a MiG-23 MEL that morning, supposedly the most capable interceptor in the Syrian inventory, equipped with Soviet radar that training officers promised could detect Israeli fighters at 50 kilometers. His radar warning receiver remained silent until the moment his wingman exploded. No missile launch warning, no indication of being targeted. He ejected over friendly territory and watched 4 more MiGs fall before his parachute deployed. Captain Walid's testimony matches Jamal's in the details that matter. Sudden catastrophic losses, radar systems showing nothing useful, ground controllers calling vectors that made no sense. Walid flew a MiG-20 UBIZ that was supposed to be nimble enough to dogfight anything the Israelis operated. He never saw the Israeli fighter that killed him, never got his radar locked, never had time to maneuver. His R-60 missiles refused to track. The infrared seekers apparently jammed or confused by countermeasures his Soviet instructors never mentioned existed. He pulled maximum Gs trying to break whatever was targeting him and watched his airspeed bleed away while the missile closed from an angle. His training said was impossible. The ground radar operators provide testimony that's even more disturbing. Syrian surveillance radars at Damascus tracked the battle, watching Israeli formations maneuver with coordination that suggested real-time information sharing across distances that should prevent tactical communication. Israeli fighters were executing coordinated attacks from opposite directions, engaging Syrian formations simultaneously from high and low altitude, maintaining perfect positioning that required situational awareness the Soviet systems couldn't provide. The radar operators watched Syrian aircraft disappear in clusters while Israeli formations remained intact, untouched, apparently invulnerable. Major Ibrahim flew one of the few MiG-23s that made it back to Damascus, his aircraft leaking hydraulic fluid from damage he never saw happen. His radar worked perfectly according to all technical indicators. The scope showed contacts, the ranging system provided numbers, the weapons system indicated ready status. But every target he locked disappeared from his scope within seconds, the tracks vanishing as if the aircraft simply ceased to exist. He fired 2 R-23 missiles at contacts his radar said were 15 kilometers away. Both missiles guided for approximately 10 seconds, then lost lock and self-destructed. He has no explanation for why Soviet missiles that worked flawlessly in training failed completely in combat. The Syrian electronic warfare officers report jamming across multiple frequencies, Israeli aircraft broadcasting interference that overwhelmed Syrian radar receivers and communication systems. Ground controllers were screaming vectors into radios that pilots couldn't hear clearly through the static. Missile guidance systems were losing lock as Israeli jammers flooded the frequencies they needed. The Syrians had trained for electronic warfare. Soviet doctrine included jamming procedures and frequency-hopping protocols. But the intensity and sophistication of Israeli countermeasures exceeded anything Soviet advisors had prepared them for. Soviet advisors reviewing the battle data offer explanations that blame Syrian execution rather than Soviet technology. Syrian pilots failed to maintain proper formation discipline. Syrian ground controllers provided inadequate tactical direction. Syrian maintenance crews didn't properly calibrate radar systems. The analysis carefully avoids confronting the obvious conclusion that American fourth-generation fighters with pulse Doppler radars, beyond visual range missiles, and integrated electronic warfare represent a technological generation that Soviet systems can't counter. The final statistics tell the story that individual testimonies can't fully capture. 82 Syrian aircraft destroyed in under 2 hours. 29 SAM batteries eliminated in the same afternoon. 0 Israeli losses to air-to-air combat. Syrian pilots who survived describe an enemy that saw them before they saw anything, that shot from ranges their training said were impossible, that coordinated across distances that should prevent tactical cooperation. They fought American technology operated by pilots who understood how to exploit every advantage those systems provided. The Syrian Air Force never recovers from June 9, 1982. Damascus cancels offensive air operations over Lebanon indefinitely, rewriting doctrine to assume Israeli air superiority rather than contest it. Syrian pilots continue training on Soviet aircraft for the next 4 decades, but the fundamental confidence that made them willing to engage Israeli formations dies in the Bekaa Valley. Future Syrian war planning treats air power as a liability to be protected rather than an asset to be employed. The psychological damage proves more permanent than the material losses. Israeli commanders draw different conclusions from the same afternoon. The combination of American fighters, American sensors, and Israeli integration has produced results that exceed even optimistic pre-battle predictions. The F-15 and F-16 prove that fourth-generation fighters don't just outperform third-generation designs. They operate in a different tactical reality, where information dominance enables engagement strategies that were theoretically impossible a decade earlier. Israeli Air Force leadership commits to American aircraft procurement for all future fighter requirements, abandoning domestic alternatives that can't match the technological sophistication McDonnell Douglas and General Dynamics achieved. American defense planners studying battle reports in Washington realize that Vietnam-era doubts about beyond visual range combat have been definitively answered. The F-15's AN/APG-63 radar achieved exactly what Hughes engineers promised: multiple simultaneous target tracking, look-down, shoot-down capability through ground clutter, reliable target identification at ranges where visual confirmation is impossible. The 78 air-to-air kills Israeli F-15s scored between 1979 and 1982 without a single loss prove that American pulse Doppler technology and AIM-7 Sparrow missiles create engagement windows that Soviet fighters and ground-controlled intercept doctrine cannot counter. Soviet military analysts reviewing Syrian debriefings face uncomfortable questions about fighter design philosophy that dominated Soviet aviation since 1950. The emphasis on ground-controlled intercept, the reliance on rigid formation discipline, the assumption that numerical superiority compensates for technological disadvantage. All of these doctrinal pillars collapsed against an enemy that achieved information dominance through sensor integration. Soviet designers begin work on fourth-generation responses, but the MiG-29 and Su-27 won't achieve operational status until the late 1980s, creating a capability gap that persists throughout the decade. Regional power dynamics shift immediately. Israeli air dominance over Lebanon becomes absolute, allowing ground operations that would be suicidal under contested skies. Syrian forces withdraw from positions they can't defend without air cover. The Syrian SA-6 network that represented billions of rubles in Soviet investment and years of installation effort becomes abandoned wreckage scattered across the Bekaa Valley. Future Syrian defense planning assumes Israeli aircraft can operate anywhere over Syria with impunity, fundamentally constraining Syrian military options for generations. The technological lessons propagate across American defense programs. The success of network-centric operations where data links share sensor information validates concepts that Pentagon planners have been advocating since the mid-1970s. The effectiveness of coordinated electronic warfare, anti-radiation missiles, and precision-guided weapons against Soviet air defense systems informs American planning for potential European conflicts. The Bekaa Valley becomes a laboratory demonstration of what fourth-generation American air power can achieve against Soviet-designed integrated air defense systems. 40 years later, the 82-0 kill ratio remains the most lopsided air combat result in modern warfare. Israeli F-15s have never suffered an air-to-air loss, a combat record spanning 4 decades and hundreds of engagements. The afternoon of June 9, 1982 represents the moment when American engineering decisively established fourth-generation fighter superiority. When Boyd's energy maneuverability theory and Hughes' pulse Doppler radars and General Dynamics fly-by-wire controls combined to create weapon systems that didn't just outperform Soviet designs, they redefined what air superiority means. Syrian pilots who survived that afternoon understand better than any analyst what happens when 1970s American technology fights 1960s Soviet systems. They watch their entire Air Force disappear in 2 hours, killed by enemies they never saw, defeated by engineering advantages they couldn't overcome and didn't know existed until it was too late.